Have you ever struggled with a really stubborn bolt? Or maybe tried wrestling with a heavy steering wheel in an old car, without power steering?
Oh, yeah, definitely.
You sort of instinctively know where to push and how hard, right? To
Yeah,
get that turning effect.
exactly.
But mechanically speaking, what exactly is going on there? What's the hidden physics behind that twist?
It's way more than just a simple push or pull, isn't it? It's really about the tendency to rotate.
Ah, okay.
And that fundamental idea, the moment, or sometimes torque, well, that's precisely what we're going to unpack today.
Absolutely. Today, we're taking a deep dive into these core ideas, forces, moments, how they make things spin or want to spin.
Right.
We'll explore how engineers, simplify really complex systems to understand these turning effects. Could be a wrench on a bolt, forces on a crane, even winds pushing on a big sign.
Uh-huh.
Our mission here is to give you a shortcut to being well informed on this, maybe find some surprising facts, and, well, hopefully keep it interesting.
And for this deep dive, we've really distilled things down from a pretty comprehensive textbook on force system resultants. We pulled out the key definitions, the main formulas, and some real-world applications.
Just the good stuff.
Basically, yeah, to give you the clearest, most practical understanding we can.
Okay, let's start right at the beginning then. The moment of a force, sort of the scalar version first.
Sounds good.
So a moment. You can think of it as the measure of how much a force wants to make something rotate around a point.
Right, a pivot point. And people often call it torque, too, which might ring a bell for some listeners.
Yeah, torque's probably more familiar.
Think about that wrench again. Trying to loosen a bolt, you push down on the handle, right? You're not pushing at the bolt, you're pushing some distance away from its center.
Right, out on the handle.
And that makes it want to spin around that center point. That tendency, that's the moment.
And the strength of this turning effect, the moment's magnitude, it seems pretty intuitive. It kind of boils down to two things.
It does. How hard you push, that's the force, F,
Okay.
and how far away from the pivot point you push, but crucially, the perpendicular distance.
The perpendicular part, that's the key bit.
That's the key bit. We call that the moment arm, usually denoted by D.
So the moment, MO, is just force times that perpendicular distance, DMO equals F times D.
Exactly. The stronger the force, or the longer that moment arm, the bigger the turning effect.
Which is why you instinctively grab a wrench right at the end. You're maximizing D.
Precisely. And if you push at an angle, well, only the part of your force that's perpendicular to the wrench actually helps turn it.
So your effective moment arm gets shorter.
Right. It's like D times the sine of the angle. It's harder to turn.
And if you push straight along the wrench, towards or away from the bolt.
Then your moment arm is 0. No perpendicular distance, no turning effect at all.
Okay, makes sense. So the units reflect that. Force times distance. Newton meters or pound-feet.
Yep, N or lb/ft.
Now, what about direction? Clockwise, counterclockwise. How do we define that consistently?
Yeah, good question. We use the right-hand rule. It's super handy.
Okay, how's that work?
Imagine curling the fingers of your right hand in the direction the thing wants to rotate.
Okay, got it.
Your thumb then points in the direction of the moment vector. Conventionally, if your thumb points out, say, out of the page towards you, that's usually positive, counterclockwise.
And if it points into the page?
That's negative, clockwise rotation.
Gotcha. So if you have a bunch of forces acting on something, but it's all flat, like 2D.
Then finding the total turning effect, the resultant moment, is pretty straightforward. You just add up all the individual moments algebraically.
So keeping track of the pluses and minuses for counterclockwise and clockwise.
Exactly. Positive moments add, negative moments subtract. Simple addition.
All right. That seems manageable for 2D, but the real world isn't always flat, is it? What happens when things get three-dimensional?
Yeah, here's where it gets, well, more interesting and maybe a bit trickier.
Because visualizing that perpendicular distance, that moment, arm D, in 3D space, that sounds tough.
It can be incredibly difficult, sometimes almost impossible without some serious geometry gymnastics.
So how do engineers handle that?
This is where vector algebra becomes, frankly, indispensable. Specifically, something called the cross product.
The cross product, okay.
Yeah.
I remember that from physics, kind of.
Right. So the cross product of two vectors, let's call them A and B, written AXB, it doesn't give you a number.
It gives you another vector, right?
Exactly. It gives you a third vector, let's call it C, and this vector C is perfectly perpendicular to both A and B.
Okay, perpendicular to the plane they define.
Precisely. Its magnitude, the length of C, depends on the lengths of A and B and the sine of the angle between them. C equals A, B sine the theta.
And its direction. Still the right-hand rule.
You got it. Another application. Curl the fingers of your right hand from the first vector A towards the second vector B.
And my thumb points in the direction of C, the cross product.
That's the one.
Now, I seem to remember something important about the order, like A cross B versus B cross A.
Ah, yes. Crucial point. The cross product is not commutative. That means order matters. Big time.
So AXB isn't the same as BXA.
Nope. In fact, AXB is the negative of BXA. They have the same magnitude, but point in exactly opposite directions.
Okay, that's definitely something to watch out for. So how does this vector magic apply to moments in 3D?
It makes the definition really elegant. The moment of a force F about a point O, written MO, is simply the cross product of a position vector R and the force vector F.
MO equals R cross F.
MO equals RXF. That's the vector formulation.
And what exactly is this R vector? Where does it go from and to?
R is a position vector. It starts at the point you're calculating the moment about, point O.
Okay.
And it goes to any point along the line of action of the force F.
Any point on the line. That seems flexible.
It is, and that's connected to something fundamental. But first, what's really neat is that if you calculate the magnitude of this RXF...
Which would be R times F times sine of the angle between them.
Right. It still mathematically works out to be F times D, where D is that perpendicular distance we talked about earlier.
So the vector method gives the same magnitude as the scalar method.
It does. It's consistent. Just a more powerful tool for 3D.
You mentioned going to any point on the line of action connects to something fundamental.
Yes, the principle of transmissibility. Basically, because R can point anywhere along the force's line, it mathematically proves that you can slide the force vector F anywhere along its line of action.
Like pushing it further up the line or pulling it back down.
Exactly. And it will still produce the exact same moment about point O. The turning effect doesn't change just because you moved the force along its own line.
That sounds incredibly useful for simplifying problems.
Oh, it is. Engineers use it all the time.
Now, there's another principle, Varignon's theorem, or the principle of moments. How does that fit in?
Varignon's theorem is another really useful tool, especially sometimes even in 2D. It states that the moment of a force about a point is equal to the sum of the moments of its components about that same point.
So instead of finding the moment of the whole force F.
You can break F down, say, into its x and y components, fx and I phi. Then you calculate the moment caused by s about the point, and the moment caused by phi about the point, and just add those two moments together.
And that gives you the same result as the moment of the original force F?
Exactly the same result. MO equals RXF is the same as MO equals RXF1 plus F2, which equals RXF1 plus RXF2. The vector math proves it works.
Why would you do that? Is it easier sometimes?
Often, yes. Especially in 2D. Finding that tricky perpendicular distance can be a pain geometrically.
Right.
But finding the x and y components of the force and their simple lever arms, which are just x and y coordinates relative to the pivot, that's usually much easier. The formula often boils down to MO Fx times y minus phi times x.
Ah, so you trade finding one tricky distance for finding two simpler moments from components.
Precisely. It's often a very convenient calculation shortcut. Our source material has examples showing just how much easier it can be.
Okay, that makes sense. Now, what about sometimes you don't care about the total moment, right? Just the moment about one specific axis.
Exactly. Great point. Think about loosening a lug nut on a car tire with a wrench.
Okay.
You applied force. The wrench creates a moment vector, probably pointing in some awkward 3D direction.
Right.
But the lug nut itself, it can only rotate about one line the axis of the bolt. Let's say it's the axis.
So you only care about the part of the moment that's actually turning it around that axis.
Precisely. We need the component of the total moment vector MO that lies along the specified axis.
How do we find that? Is there a simple way, like the scalar F thing?
Sometimes. If the geometry is really clear and you can figure out the shortest perpendicular distance, let's call it d, directly from the force's line of action to the axis itself.
Not just to a point, but to the whole line.
Right, to the axis line. Then the moment about that axis, ma, is just f times that distance, d. Ma, f, d.
But I bet that day is often hard to find in 3D.
You bet correctly. It often is. Which brings us back to vectors for the more general, robust solution.
So there's a vector way to get the moment about a specific axis, too.
Yes, and it involves something called the scalar triple product. Sounds fancy, but it's very systematic.
Scalar triple product. Okay, lay it on me.
You need three vectors. First, a unit vector, UA, that just defines the direction of the axis you care about.
Okay, a vector of length, one pointing along the axis.
Second, A position vector, r, that goes from any point on the axis
Any point on the axis line.
to any point on the line of action of the force F.
Got it. R from axis to force line.
And third, the force vector F itself.
Okay, U, A, R, and F. Then what?
The moment about the axis ma is calculated as UA dot R cross F.
So you take the cross product of R and F first, which gives the total moment vector MO.
Right.
And then you take the dot product of the axis vector UA with that moment vector.
Right. Exactly. The dot product projects the total moment vector onto the axis direction, giving you just the component along that axis.
And the result is a scalar, a single number.
Yes. Hence the name scalar triple product. It gives you the magnitude of the moment about that specific axis. There's a determinant form calculation that makes it pretty easy to compute once you have the components of U, A, R, and F.
What about the sign of that result? Does a positive or negative ma tell us something?
It does. If ma comes out positive, it means the moment about the axis acts in the same direction as your chosen unit vector UA.
Okay.
If ma is negative, the moment acts in the opposite direction along the axis. You can use the right-hand rule again. Point your thumb in the direction of ma, positive or negative. Your curled fingers show the direction of the twisting tendency around that axis.
Right, so it tells you whether it's trying to tighten or loosen the lug nut in our example.
Precisely.
Okay. So we've handled single forces creating moments. But you mentioned something earlier. What if you have two forces that sort of balance out in pushing or pulling, but still create rotation?
Ah, yes. That leads us to a very special concept. The couple and the couple moment.
A couple. What defines that?
A couple is a specific setup. Two parallel forces. They have to have the exact same magnitude.
Okay, equal strength.
But they act in opposite directions, and they're separated by some perpendicular distance, let's call it d.
So, like, one pushes north with 10 newtons, the other pushes south with 10 newtons, a meter apart.
Perfect example. Now, what's the net force of that system? If you add those two force vectors together...
10 north plus 10 south.
Yeah.
They cancel out. The net force is 0.
Exactly. The resultant force of a couple is always 0, which is fascinating because it still does something.
If it's not pushing or pulling the object overall, what's the only effect it can have?
Pure rotation. Or a tendency for pure rotation. It doesn't translate the object, it just tries to spin it.
Like turning a steering wheel with both hands. One pushes up, one pulls down.
Classic example. You're applying a couple to the steering wheel. You're not trying to push the whole wheel forwards or backwards, just make it turn.
Okay, so that pair of forces creates a turning effect, which we call the couple moment M.
Right. And here's the really key insight about couple moments. They are free vectors.
Free vectors. What does that mean?
It means the turning effect produced by that couple is the same no matter where on the body you consider it to be acting.
Wait, unlike the moment from a single force, which depends on the pivot point O.
Exactly. A couple moment isn't tied to a specific pivot point. Its rotational effect is the same everywhere on the object. You can slide that couple moment vector anywhere, and it represents the same pure twist.
Wow, okay. That's a big difference. How do you calculate its magnitude?
Simpler than the single force moment, actually. The magnitude of the couple moment M is just the magnitude of one of the forces, F, times the perpendicular distance d between their lines of action, MFD.
Just F times D. Nice and easy. And the direction.
Still our friend, the right-hand rule. Curl your fingers in the direction the couple wants to make the object spin, and your thumb points in the direction of the couple moment vector M, which will be perpendicular to the plane containing the two forces.
Got it. So different forces and distances can make the same couple moment, right?
Absolutely. A 30 Newton force pair 0.4 meters apart gives M equals 3, 0.4 equals 12 Newton meters.
Okay.
And a 40 Newton force pair 0.3 meters apart gives M equals 40, 0.3 equals 12 Newton meters. Same magnitude, same direction, assuming the rotation sense is the same. They are equivalent couples.
And because they're free vectors, if you have multiple couples acting on a body,
You just add their moment vectors together using standard vector addition. It simplifies things hugely.
right. Now, let's zoom out. Real-world engineering problems.
Well,
You really have just one force or one couple, right?
yeah.
You have a whole mess of things acting on a structure or a machine part.
Oh, yeah. Usually it's a whole system of forces acting at different points, maybe some couple moments thrown in there too. It can look pretty chaotic.
So what's the engineer's strategy? How do you deal with that complexity? You need to simplify it somehow.
That's the goal. We need to find an equivalent system that's much simpler, but has the exact same overall effect on the body's motion or its support reactions.
An equivalent system, what does that usually look like?
The standard approach is to reduce the entire complex system down to just two things, acting at a specific point O that you choose.
Okay, two things.
One, a single resultant force, FR, and two, a single resultant couple moment, usually written MRO.
So the whole complicated mess gets replaced by one force and one twist at point O.
Exactly. And this simplified FR and MRO system will produce the same external effects as the original messy system.
How do you find FR and MRO?
FR, the resultant force, is pretty straightforward. It's just the vector sum of all the individual forces acting on the body. Sum up all the F vectors, FR equals 5.
Just add up all the pushes and pulls victorially.
Got it.
What about the resultant couple moment, MRO?
That takes a bit more work. You have to do two sums. First, sum the moments of all the individual forces about your chosen point O using MO equals RXF for each one.
Okay, sum of moments from forces about O.
Second, you just add up all the actual couple moments that were already acting on the body. Remember, those are free vectors, so they just add in.
So MRO plus RXF plus MA.
Precisely. Sum of moments about O plus the sum of pure couples.
Now, you said you choose point O. Does the result change if I choose a different point, say point P?
Good question. The resultant force, FR, will be exactly the same regardless of which point you choose. The total push-pull doesn't change,
Okay.
but the resultant couple moment will generally change. MRO will be different from MRP.
Why is that?
Because there are vectors used to calculate the moments of the individual forces, the RXF part, are measured from that reference point, O or P. Change the reference point, you change those R vectors, and thus you change the sum of those moments. The mem part, pure couples, stays the same, though.
Ah, okay. That makes sense. This actually leads to an interesting question. How do you, mathematically move a force from its line of action to a different point, say point O, while keeping the system equivalent?
This is a really neat concept, sort of the aha moment for understanding simplification. Let's say you have a force F acting at point A, and you want to represent its effect at point O instead.
Okay.
What you do is, at point O, you add two forces. One force equal to F, another force equal to F, same magnitude, opposite direction.
Adding F and FF at the same point O, that has zero net effect, right? So you haven't actually changed anything overall.
Exactly, you've added zero net force.
Mm-hmm.
But look what you have now, the original F at point A and F at point O. Now pair the original F at A with the NSF force at O. What do you have?
Equal magnitude, opposite direction, separated by a distance. It's a couple.
Bingo. Those two form a couple. And the moment of that couple is M equals F times D, where D is the perpendicular distance between the original line of action and point O. And what's left? You still have the force F acting at point O.
So moving the force F from A to O is equivalent to having the force F acting at O, PLUS, adding a couple moment M equal FD.
That's exactly it. It shows why when you move a force, you generally have to introduce a couple moment to maintain equivalence. It's not just magic. It comes from adding that balanced pair of forces.
That really clarifies things.
Mm-hmm.
So we can always reduce a system to FR and MRO at some point O. Can we ever simplify it even further, like get rid of the couple moment entirely?
Sometimes, yes. You can reduce the system to just a single resultant force, FR, acting along a specific line with no couple moment needed.
When is that possible?
That magical simplification happens if the resultant force, FR, and the resultant couple moment, MRO, calculated relative to some point O, happen to be perpendicular to each other. FR, MRO.
Perpendicular. Okay. Does that happen often?
It happens in several common and important cases. For example,
Like what?
concurrent force systems where all the forces' lines of action pass through a single point. The moments about that point are all zero, so MRO is zero. Easy.
Makes sense.
Coplanar force systems where all the forces lie in the same plane. The resultant force, FR, will be in that plane, but all the moments and the resultant moment will be perpendicular to the plane. So FR and MRO are always perpendicular.
Okay. Plane forces, perpendicular moment.
And parallel force systems where all forces are parallel, say, to the z-axis. FR will be along the z-axis, but the moments they create will be about the x and y-axis, making MRO perpendicular to FR.
Like weights hanging off a beam. They're all parallel downwards.
Perfect example. You can replace all those individual weights with a single equivalent total weight acting at one specific point along the beam, and it produces the same total force and the same total turning effect moment about any point.
So for those cases, you find FR, and then you figure out where to put FR so that it creates the same moment MRO as the original system did.
Exactly. You solve for the location of FR's line of action.
What if FR and MRO are not perpendicular? Like in a general messy 3D force system.
Yeah.
Can you simplify that further than FR and MRO at a point?
You can simplify it one more step to something called a wrench or sometimes a screw.
A wrench.
Yeah. In the general case, you can always resolve the resultant couple moment, MRO, into two components. One parallel to the resultant force FR and one perpendicular to it.
Okay.
You can eliminate the perpendicular component of the moment by shifting the line of action of FR, just like we discussed for the coplanar parallel cases.
Right.
What you're left with is the resultant force FR and a couple moment component that is collinear with FR, meaning the moment vector points along the same line as the force vector.
So a force and a moment acting along the same axis.
Exactly. That combination, a force and a collinear couple moment, is called a wrench. It represents both a push-pull and a twist along a single specific line in space. That's the simplest possible representation for a general 3D force system.
Fascinating. A push and a twist, like turning a screw. Hence the name wrench or screw. Okay, one last major topic from the outline. We've talked a lot about forces acting at points or couples, but what about loads that are spread out? Like not concentrated?
Right, distributed loadings. Very important in real structures. We often simplify loads to point forces for analysis, but reality is often spread out.
Give me some examples.
Think of the pressure of wind acting across the entire face of a large billboard sign.
Okay, yeah, it's not just pushing on one spot.
Or the pressure of water pushing against a dam. It's stronger at the bottom, weaker at the top, but distributed over the whole surface. Or even just the weight of, say, a pile of gravel or snow spread over a roof surface.
Those are definitely not point forces. How do we handle those? Let's focus on, say, loads spread along a line, like pressure on a beam.
Good idea. Coplanar distributed loads, usually represented by a function, Wx, telling you the force per unit length, like newtons per meter, at any position x along the beam.
So the loading can vary along the length, like a triangle shape or a trapezoid?
Exactly. It could be uniform, rectangular shape, triangular, trapezoidal, or some other function Wx.
Can we still simplify this distributed load, like we did with multiple point forces?
Yes. Remarkably, the external effects of any distributed load Wx along a line can be represented by a single equivalent resultant force Fr.
Just one force again? How do you find its magnitude?
This connects nicely to calculus, actually. If we connect this to the bigger picture, the magnitude of this resultant force, Fr, is simply equal to the total area under the loading diagram, Wx.
The area under the curve. So if the load is Wx newtons per meter over a length L meters, I integrate Wx dx from 0 to L.
Exactly. Fr eduates dx, which is just the area.
Okay.
For simple shapes like rectangles or triangles, you don't even need calculus, just use basic geometry. Area of rectangle is base times height. Area of triangle is half base times height.
Okay, so magnitude is the area.
Yeah.
But where does this single force Fr act? Its location must matter for the turning effect, the moment.
Absolutely critical. This resultant force Fr must be placed so that its line of action passes through the centroid of the area under the loading diagram.
The centroid, that's
Yeah.
like the geometric center of the shape defined by Wx.
Precisely. For a uniform rectangular load, the centroid is right in the middle. For a triangular load, it's 1/3 of the way along the base from the tall end.
And there's a formula for the centroid's position, x bar.
Yes, involving integrals, again in the general case, x Wx dx, Wx dx. The top part is called the first moment of area. The bottom part is just the area, Fr.
But again, for simple shapes, we probably know where the centroid is without integrating.
That's the practical approach. Break down complex load shapes, like a trapezoid, into simply rectangles and triangles. Find the resultant force, area, and centroid location for each simple shape. Then combine those resultant forces to find the overall resultant force and its final location. Much more manageable.
So even spread out loads can be simplified down to a single equivalent force acting at the right spot.
For the purpose of finding external reactions, yes, it's a hugely powerful simplification technique.
Wow. Okay, so we've really covered a lot of ground here. We journeyed from like the basic idea of a force making something want to turn,
Right, the moment of a single force.
all the way through 3D vectors, cross products, moments about axes, these special things called couples.
And how engineers cleverly simplify whole systems of forces and moments down to maybe just one force and one couple moment, or sometimes even less.
And finally, tackling those distributed loads by finding an equivalent single force acting at the centroid. We saw how precise definitions, vector math, and these smart simplifications let engineers model the real world.
Turning messy reality into problems you can actually solve, yeah.
So why does all this matter to you, the listener? Well, understanding moments, couples, resultants. It means you're not just, passively observing anymore.
You're analyzing. You're seeing the hidden mechanics behind everyday actions and engineered structures.
Exactly. The next time you twist a jar lid, or push open a heavy door, or maybe see a huge construction crane lifting a steel beam,
You'll have a much better grasp of the principles at play, the forces involved, the crucial moment arms, the resulting turning effects, maybe even the couples being used.
you'll kind of see the invisible levers and twists in action all around you.
So here's something to think about. What does this all mean for how you see the world now? How might this deeper feel for moments and force systems change your perception?
Yeah, maybe how you look at the design of a simple tool, like even a nutcracker or pliers, or think about the stability of a tall building against the wind, or a bridge handling traffic.
What surprising moments, pun intended, maybe might you notice now, in bridges, in tools, in your own body mechanics, now that you understand a bit more about the why behind the turn?